electron hole pair. Just with heat, you get a few. And when we get those, we write them like this, Ni. But at room temperature or any temperature, number of holes will be always exactly same as number of electrons, right? They're coming from electron hole pair formation. So we can use one variable to denote them. We can just write Ni. Ni, if you see Ni, you would always know this is intrinsic charge carrier concentration. When I say charge carrier, I'm not saying electron, I'm not saying hole, I'm saying charge carrier because that means both equal. How much is for silicon? I just told you guys a few slides ago. So it's 1.5 times 10 raised to power 10 per centimeter cube. That's the Ni value for silicon. Always we use this. So we have these values for other materials also. So what does this mean is that in silicon, there will be always this many electrons and exact same number of holes available. In pure silicon, there's no impurity, there's no defect, and there's no uh, outside help for electrons to be excited, right? There's no light shining on it, no heat and everything, nothing. So that would be the value. But when we talk about it, there's a couple of things we say. We say there is a rate of generation. For EHP, we say it's GI. And there is a rate of recombination because those electrons are jumping back to the valence band as well. We call it GI. So at equilibrium, Ri is equal to GI. As many numbers are generated, same number is being recombining, right? But they both have dependence on temperature, so we can write them as GI sub T and Ri sub T. So we can say when the temperature increases, Ri and GI both go up, right? So to from this idea that Ri depends on how many electrons or holes are there, we can write a simple relationship where we write this alpha R, which is the uh, rate of recombination, I think. So hold on. So this is used to tell us that how fast is that relationship occurring or how fast they are coming back and binding with each other. It's a constant of proportionality, which just tells us that how fast are they, how fast is that reaction occurring for them to recombine. It's alpha sub R. Now, once we add outside things, we are adding helpers. Either we are adding uh, those things that can contribute to electrons, or we are adding those things that can contribute to holes. If you go back to basic chart, silicon or this group 4 elements, they have 4 electrons in their outermost shells, which means they can get 4 more and they can fill their outermost shell. Or we can just add a material that can add 1 more extra. Or we can add a material that has 1 less in the outermost shell. So both cases are what we call as N-type or P-type donors. And same is the thing for the germanium, carbon, silicon, germanium. So compound semiconductors also have the same thing, that on average, they have 4 valence electrons per atom. Now, when we add external impurities, we call that material as extrinsic material, extrinsic semiconductor material. And this process happens what we call by doping. So it's achieved by doping, in which we introduce the outside materials, and that helps us vary the conductivity. When doping happens, the carrier concentration is no more written as Ni or Pi. It would be written as N naught or P naught. But you have to remember, if you are introducing an N-type semiconductor, then we are only changing N. So Ni would be then becoming N naught. But Pi would stay what it was. There'll be no change in Pi. This is when we are doing N-type doping. Agree with me, right? So when we are doing N-type doping, we are only changing the electron concentration. There's no change in hole concentration. And vice versa. If we are using a P-type material, we are doing P-type doping, we are only changing hole concentration and electron concentration stays the same at intrinsic levels. All right, so a couple of things and we'll stop. So when we do that, we introduce energy levels either close to conduction band or close to valence band. So we'll come to this later on. Right now, I just wanted to share this, that by introduction of those new levels of energy levels, either close to conduction band, which would be N-type, or close to valence band, which would be P-type. So if I go back to this one, so what we are doing here is either we are introducing either right now I want to focus on either we are introducing close to conduction band, that's N-type, or we are introducing close to valence band, these are called P-types. So let's focus on P-type only by if we introduce this. So what we are doing is now we have introduced, we have provided more sites for electrons. Now think about it, if an electron jumps from here and if an electron jumps for here, which one is easier to do? From the valence band level or from the this EA level? Right? The EA level is easier,
Yeah.
less energy. So, and same argument is for the N-type energy level that's been is added there. So if this is added, they just have to oh, they just have to get to this point, and that would be it. They don't have to go all the way. They don't have to go all the way in there. So that's essentially a kind of a graphical representation of energy changes, what happens there. So now when we apply temperature, then this is the N-type example. They would be available right close to it. And these are N-type uh, examples: phosphorus, arsenic, antimony, vanadium. So these are few examples of N-type semiconductor dopants. We call these donor materials because they are contributing extra electrons to the system, to the material, to the semiconductor material. In the same way, this would be happening for uh, acceptor materials, P-type materials. In this case now, we have provided extra energy level close to the valence band. When that happens, we are getting similarly, they are easy to jump from EA to conduction band. And these are the examples of boron, aluminum, gallium. Oh, that was not vanadium. That was group 5. Sorry, I mistook that. So this is group 5. And on the previous slide, it was group 3. Sorry, group 5. Yeah, so this is group 5. All right, questions?
Is sandwich?
All right, let's stop here. It's just the basic introduction of extrinsic materials and intrinsic materials. And within extrinsic materials, dopants, N-type dopant, P-type dopant. P-type dopant would add a hole, and N-type dopant would add an electron to the system. So N-type case, you'll have now many more free electrons that will be available. In the other case, you'll have many more holes that will be available for conductivity.